everyone. Here in this talk, I'm showing you the inverse scattering series internal multiple attenuation in an absorptive dispersive earth without needing or estimating elastic or inelastic subsurface properties. And I will update you with the preset data examples. My talk is seen in this part to look at the internal multiple attenuation algorithm or data with Q absorption. So the inverse scattering series says that you can achieve every processing objective directly and without subsurface information. And from the paper by Weglein and his colleague in 2003, it's understood that for both free surface multiple and internal multiple, those subsurfaces not only don't care about the subsurface information, they don't care what kind of model type you have in mind. Since you can change your Earth model to be acoustic, elastic, or what I will show you is inelastic. All those algorithms don't need to change even one line of your code. In other words, for both free surface multiple eliminator and the internal multiple attenuator, those algorithms are always the same, no matter what kind of model type you have. And this is what model type independence communicates. Okay. So next, I'd like to use this chart to explicitly show you how ISS internal multiple attenuator performs for different Earth model type. So first, if your Earth model is acoustic heterogeneous, and by using homogeneous acoustic background, Rujo, Weglein, and other colleagues prove that the ISS attenuator can effectively predict the internal multiple with the perfect time and approximate amplitude. And for the elastic heterogeneous work, it's very interesting because based on the work by Coase and Weglein in 1996, they found that even use a homogeneous acoustic reference medium, they can effectively predict the converted internal multiples. That's dramatic because you give a wrong model but have a satisfying output. Okay, so now what about the inelastic heterogeneous medium? And in this world, you will have your propagating wave with absorption, and the velocity is dispersive. And what will happen for this internal multiple attenuator? And there is a general proof from those from the 2003 paper mentions that the internal multiple attenuation algorithm is model type independent. But here in this talk, this is the first time I'm going to show you with the analytical example to see give the word to be inelastic and to say absorptive and dispersive. But the ISS attenuator just use a homogeneous acoustic background to see what happens. And a reasonable question here is why do we look at this? Because you are often part of the world that the inelastic property is significant. For example, in the pre-salt areas in deep water Gulf of Mexico, or Red Sea, or North Sea, in those areas, those inelastic property is very significant. And under this circumstance, you like to have confidence that just even in a world with absorptive and dispersive, you don't need to specify all those properties. Just apply the ISS attenuation algorithm, and that algorithm will maintain its effectiveness, finish what it commitment, give you the exact time and approximate amplitude. And I hope this talk can give you that confidence. Okay, so this is the outline here. First, I will show you the analytical examination, and after that, I will show you two specific examples to see what happens. And after that, I will show you our plan towards internal multiple elimination, and the end is the summary. Okay, let's look at the first part. And in this part, I will give you the model. Then we can analytically express both primary and the internal multiples. And after that, we can put this analytical data into the ISS internal multiple attenuation algorithm to have the analytical prediction result. And after that, we can analytically compare the prediction result and the actual internal multiple of your data to see what happens. And here I'd like to remind you, here we gave the model because we need to use this model to generate the data. But later in a minute, you will see that our ISS attenuation algorithm doesn't take this information. Okay, so first let me show you how do we express the wave field. And here we consider a constant Q model proposed by Polsky, and take a 1D case as an example. Then we can express the wave field using this wave equation. Here P is the pressure wave field, and the F of omega is a factor. It consists these two terms. The first term is related to the energy absorption, and the second term is related to the velocity dispersion. So here we define a frequency-dependent velocity here, and we can use this velocity to express our wave field. And if we look inside, it contains these three terms. And the second term is contributing to the energy absorption, and the third term is contributing to the velocity dispersion. So here we can see if we increase Q to infinity, and this will back to the elastic or acoustic case. Okay, next we will use this expression to express our primary and internal multiple. Okay, next we like to test the ISS attenuation algorithm. And well, the ISS attenuation algorithm is designed for both 1D and multi-D case. But here, for simplicity, I just show you the 1D normal instance case. And we use a true reflector model here, and assume the free surface multiple is removed, and we locate both the source and receiver are at depth 0. And these are their parameters, the frequency-dependent velocity, the density, and the quality factor. And I'd like to remind you again, this factor here, because we need to generate the data. And so now in your data D of T, you will have these two primaries, P1 and P2. And here R is the reflection coefficient, and the T is the transmission coefficient. Okay, so now we have our data. We do the transform. We can transform the data from time domain to the frequency domain. And in the frequency domain, we can analytically express these two primaries by using the way we saw a minute ago. Okay, so both these events are suffering from the absorption and the dispersion here. So next, we transform the basis of the variables from the frequency to the vertical wave number Kz here. And one very important thing I'd like you to pay attention here is when we do the map, we just use a constant velocity C0 here. In other words, the ISS attenuation algorithm just take its background as a homogeneous acoustic medium. So that's the key point here. And after that, we do the stalled migration to transform the data from the vertical wave number domain to the pseudo depth domain. And because we use the constant velocity to do the migration, so in the pseudo depth domain, the actual depth relationship will be kept. In other words, actually the first primary is generated at a lower depth, at a shallower depth than the second primary. So now in the pseudo depth domain, this relationship will be kept. Okay, so now with B1Z, we can apply the ISS internal multiple attenuation algorithm to have our predicted internal multiple in the vertical wave number domain. And after that, we can transform the data back to the time domain to have our final prediction. Okay, so this is the integral formula. Let's look inside. There are 3 B1 here. These 3 B1 are corresponding to these 3 events here. And we can see that in the integral limit, there is epsilon. The epsilon here is used to make sure these three events satisfy deeper, shallower, and deeper relationship in the pseudo-depth domain. And as I mentioned, because we do use the constant velocity for the salt migration, and its actual depth relationship is kept here. So, in another word, in the actual world, these three events is generated at the deeper and shallower and the deeper depths here. Okay, now we go through the calculation. We'll have the analytic result of your predicted intermultiple B3. And as I mentioned, we can analytically express the actual intermultiple of your data. So now we compare this predicted intermultiple with the actual intermultiple of your data. We will have this relationship. And if we look at, there are two terms, and we just read in different colors. Here, the first blue term, we call this the transmission factor TF. And the TF here is related to the transmission loss at the layers above and on the interface that your multiple has its downward reflection. So for this specific example, your multiple is generated at the first interface. So only the transmission loss at the first interface is overestimated or is contributing to this term. And the second term here is the Q absorption factor. We can see this. This term is related to the absorption of the transmission loss in the layers down to the interface that your multiple is generated. So for this example, again, only the transmission loss in the first layer is overestimated. Okay, so now with both TF and the QF, we can see that the global transmission loss, including the layer and the interface, will be overestimated in this result. Since both of these TF and the QF are smaller than 1, so they will cooperate to make the prediction amplitude to be approximate or smaller to the actual amplitude, but the time is exact. Okay. So for purpose, I just use this simple 1D normal instance 2-layer to show you what happens. But this property will be preserved if you have 1D normal instance with multi-layers or multi-D as well. And if you are interested in that, I refer you to my own short note in this year's annual report. Okay, so at the end of this part, I like to remind you that I give the data goes through the absorption and the dispersion, but the ISS attenuation algorithm doesn't have all those information. Remember that constant C0, it just uses a constant acoustic as its background. And given all that, you can predict your internal multiple with the exact time and approximate amplitude. That's amazing. Okay, so next I'd like to use two specific examples to numerically examine this algorithm. And the first specific example is the 1D normal instance plane wave. Here we use a two reflector model here, and we use this model to generate the data. Okay, so with this two reflector model, we will have two primaries and one first order internal multiples in your data. And I plot this with this blue line here, two primaries and one first order internal multiple. And the red line here is the internal multiple prediction result. And now we extract the internal multiple to see detail. Okay, again, the blue line is the actual internal multiple of your data, and the red line here is your predicted internal multiple. It's very clear to see that the time is exact and the amplitude is approximate. So now we have the same conclusion as the previous analytical examination, right? Okay, the next specific example, I use 1D Earth pre-stack data. And this test was performed during my internship at Schlumberger under the supervision of Clement. And here we use a full reflector model. And given this full reflector model, we'll have the left panel is our original data with Q absorption. And again, I'd like to remind you, this data was generated using the software of Schlumberger by applying the reflectivity method. And we have these 4 primaries here, and all the other events here are the internal multiples, and they are indicated by these blue arrows. Okay, the red panel is the prediction result, and we compare the right panel with the left panel. You can see all these times are matching very well, and the energy is a little bit weak. Okay, now we extract 2 traces to see detail. Okay. So this one trace is a 0 offset, and the other is a 5 offset data. So this is the original data, and these green arrows are pointing to the first order internal multiples, and this is the prediction result. So you can see for all these 3 first order internal multiple, they give the perfect time and approximate amplitude. So the third time you see the same conclusion. And the other thing I'd like to mention here is, if you look at this part, this is the false primaries, and our prediction never touched this primary here. And okay, so until now we have seen that analytical and numerical examination, and we found that we can see the attenuator is finishing what it is expected to finish in the inelastic world. So next, I'd like to show you our idea of elimination. And here I give you 2 situations. The first situation is if the Earth, if the inelastic property of the Earth is not significant, or you can treat the Earth as the elastic Earth. Then applying the ISS attenuator, you will have this prediction result. Here again, B3 here is the predicted internal multiple, and IM here is the actual internal multiple of your data. So you can see only TF is existing here, and I'd like to remind you, TF is the transmission loss at the interfaces above and on the interface that your multiple is generated. And my colleague Yang-Li Zhou provides the elimination algorithm, and in this afternoon he will show you his very impressive result. Okay, so the next situation is if your Earth is suffering from significant inelastic property, and based on our analysis, we'll have this result. So the global transmission loss done to the interface that your multiple is generated is overestimated. And we have different plans to provide the eliminator. The first option is we look inside the inverse scaling series, and to develop the elimination algorithm in inelastic media directly. And the second option is we can do the set of pre-processing for Q compensation. So we transform the data from the inelastic world to the corresponding data in the elastic world. Then we can apply Yang-Li's elimination algorithm for the elastic media. And to do the Q compensation, we also have different choice. First, we can do Q compensation with Q if you have the Q information. And the second option is we can do Q compensation without Q. And Inan and Lira was working on this subject within our group. And here I'd like to show you one of their results. And the above picture is the data with Q absorption, and you can see the second primary is, has a smaller amplitude, but after applying the inverse scaling series Q compensation without the Q method, you can easily to see the amplitude is boosted. Okay, so until now we have seen how internal multiple attenuation algorithm performs for data with Q absorption, and I'd like to give you my summary. And first, this work is contributed to the understanding of the ISS attenuator is model type independent, which is provided by Weglein and his colleagues. And the second is if you are applying the inverse scaling series internal multiple attenuation algorithm in case where the word is absorptive and dispersive, you're gonna have confidence that the time will be predicted exactly and the amplitude will be approximate. Okay, if you are considering about the eliminator, there are different options are being thought about within our group to move the algorithm beyond the attenuation in the inelastic world, and by using some form of Q compensation with Q or without Q, and we will keep you posted on this progress. Okay, at the end, I'd like to thank our sponsors for their encouragement and for their support. And I'd like to thank Clement and Deborah and James for their excellent mentoring and guidance during my internship. And I also very much appreciate the second opportunity in this summer. Okay, at the end, thank you for attention.